Hey, so our third speaker is Maxence from Telecom Paris, and he'll be talking about fast private and regulated payments in asynchronous networks. Please.
Good morning, everyone. Thank you for the introduction. So yeah, I'm going to talk about fast private and regulated payment system in asynchronous networks, which was a joint collaboration with colleagues from Telecom Paris. So just to break down a little bit in the title and give some goals of our work, we try to design a payment system that addresses 4 different dimensions. The first one is responsiveness, since the payment system is working on in asynchronous networks. The second one is privacy. Privacy for the users, which guarantees that when they make payment or receive payment, their identity isn't leaked. And confidentiality for the payments, which guarantees that the amount of payments is hidden. Performance, since we want to design a payment system that can be used in practical world, so high transaction throughput. And finally, regulation. One natural use case for such system is CBDC, which are, let's say, equivalent to digital cash, and they are regulated. So such systems should be able to comply with regulation if they are to be used in the real world. So this presentation, we go through first the specification for the distributed object that we use, which is a fully private asset transfer. And then I will describe PaxPay, which is the implementation of this specification that we designed. So about the specification, as for classical specification of a payment system, the state is just a list of balances, one for each user. We define 2 operations, an operation transfer that allows user to transfer money from their balance to another user balance. And there is an operation called balance, which returns the current amount of money that the user have. So it can only be called, or it only returns the balance of the invoker of the operation. Similarly, the safety properties that we define is what you would expect. For the transfer, it states that you can't transfer more money that you have. So in paper, it's formalized. But yeah, it basically states that when you do a transfer, it can succeed only if the value is less than the money that you received minus the money that you've spent. And okay, what might be unusual here is that for the balance, you would expect it return the exact value of the money that you've received minus the money that you spent. Here we require the value returned by balance to be less or equal than this quantity. Since we are in asynchronous networks, payments can take time to arrive, and that's the reason why we relax this constraint. And to compensate that, we add in as a liveness property that payments eventually arrives, which is again formalized in the paper, because you also have to take into account that some payments may have been done in the meantime. So. And finally, we define a privacy property. So it is formally captured by a distinguishing game, and this implies 3 sub-properties: the sender anonymity and the receiver anonymity, which both states that when a payment is made, the sender and the receiver are hidden from the other users. And confidentiality, which states that the amount of the transfer is hidden. So now let's talk about PaxPay, which is the implementation of this specification that we made. So about the model is just that we have n validators, up to 1/3 can be Byzantine. You also have a set of users that will interact with the validators to transfer funds. So user will be identified by public addresses that we denote APKU, which is the same notations as you have in the zero cash paper. The network is supposed to be asynchronous and reliable. We also suppose that there exist anonymous channels between users, so that you can send message to another user, and the user doesn't know who has sent the message. And we also leverage several cryptographic primitives, such as threshold blind signatures, zero-knowledge proofs, pseudo-random functions, and commitment schemes. So as many other payment systems, we manipulate coins, and transfer is actually an exchange of a transfer of coin. So a coin is just a tuple of three values: V, which is the value of the coin; APK, which is the address of the owner of the coin; and rho, which is the seed of the coin. And this is just an element that is used to derive the serial number used as the nullifier to prevent double spending. So again, this is similar to what is done in zero cash. I said that we are using blind signatures, so it means that if you take a coin, you can blind it, and the blinded version of the coin, you can't get any information out of it, but still you can sign the blinded version of the coin, and then from this signature you can derive a valid signature for the unblinded coin. The signature scheme is also threshold. So the threshold is 2/3 of the n validators, and when you have 2/3 of n signatures, you can aggregate the partial signatures into a certificate that is valid with respect to what is signed, which is the coin. So this slide just explains how a transfer is done. So in this example, you can see that we have 4 validators at the top. You have Alice that has 2 coins, C1 and C2, with the associated certificates, which are just aggregated signature. She wants to transfer money to 3 new users, which are just APK1, 2, and 3. So what she does, she creates 3 new coins in blue, and she will build some zero-knowledge proof that proves several things. Among them, that the new coins, they have the same value of the sum of the values of the old coins. That the old coins, that Alice knows a certificate for the old coins that is valid. So what Alice does, she derives also 2 serial numbers, SN1 and SN2, from the old coins. And she transferred this zero-knowledge proof to the validators. Validators, they just receive the proof, they verify the proof, and if it's correct, they will just make sure that the serial numbers are not already in a list that they maintain of spent serial numbers. If it's the case, it means that Alice is trying to double spend money. If it's not, it's legit. They can just add the serial numbers to the list and assign the blinded coins that they've received, because they only receive blinded version of coins. Alice, she receives several signatures for each of the new coins. She can just aggregate the signatures into a certificate and then send to each receiver of the payment the coin and the associated certificate. And now the payment is done. The receiver, they just receive the certificates and the coins, and they know that the payment is legit, and they will be able to spend the money. So I've stated in the beginning, the payment system is regulated. So we try to match the regulation defined by some central banks, and especially the European Central Bank. For instance, we define a limit on the amount of one single transfer. We also define a limit on the total amount a single user can transfer in his use of the system. We also define a sanction mechanism, which allows the regulator to freeze the assets of a user, so that the user cannot send or receive funds anymore, but without breaking the privacy guarantees that the system already offers. And finally, we provide a way for users to make proofs about their transaction history without revealing the whole transaction history. They can just prove particular statements. For instance, that their income pattern is valid. And this is especially useful for anti-money laundering, for instance. which is a requirement for the CBDC regulations. So to implement this regulation, we define another coin, another special type of coin, which is called the compliance coin. So as a regular coin, it has an address, which is the address of the owner of the compliance coin, a seed, a value, and here the value of the compliance coin is just the total amount of money that the user has transferred since the beginning of its use of the system, and a commitment which commits to, which aggregates all the transaction data of a single user. So this was the zero knowledge proof in the non-regulated case. In the regulated case, it's just almost the same. You just have to spend the compliance coin that you have at each payment and recreate a new compliance coin. So each user only have one valid compliance coin at a time, and at each transfer, it spends the old compliance coin and create a new one. And the zero knowledge proof ensures that the commitments will aggregate the transfer data so that the commitment in the compliance coin is in fact an aggregation of all the transaction data of the user since the beginning of its use of the system. And the zero knowledge proof also ensures what we stated before, that the value of the current transfer isn't exceeding certain limits, that the total value the user has spent isn't exceeding another limit, and that the receiver of the transfer are not a member of the sanction list. So this is just a proof of non-membership verified within the zero knowledge proof. So for the implementation, we used Gross16 for the zero knowledge proof, which is, which we've seen in the previous presentation, based on arithmetic circuits. The great advantage with Gross16 is that the constant time is verification, and the verification time is constant. The PRF is based on a hash function that is optimized for arithmetic circuits, and the threshold signature is based on pairings. Since we want to have the maximum transaction throughput of the system, the main bottleneck is actually the workload on the validators, because as the system works, the validators will just receive a lot of transactions. They are going to, they will need to verify the transactions, make signatures, and this is the main bottleneck for the transaction throughput. So to increase the throughput, we limit the workload of validators by verifying the certificates within the zero knowledge proof, which doesn't increase the zero knowledge proof verification time because it's constant, as we said it before. And okay, well, this just implies some stuff about the elliptic curves you can instantiate the signature and the zero knowledge proof on. And this is just the curve that we used. So to make a quick comparison with the other payment system, because there are a lot of, like a variety of payment systems that address privacy, we built this table with many additional details in the full paper. So our work is at the very right of the table. For the privacy properties, we can just state that we granted the highest standards, let's say, of privacy, as for Zcash and another payment system called UTT. For the regulation features, we mainly compared to the last two payment system, Parity and Parsecoin. We just decided not to implement a feature called full asset tracing that we called full asset tracing. That was implemented by those two papers, and we replaced it by the sanction mechanism and provable transaction history. And finally, for the performance, we did a benchmark, and it was that we, let's say, outperformed the UTT performance by a factor of 4. But the main drawback of our implementation is the proving time of the zero knowledge proof. So this is the workload of the users that is quite high. For on one core of the CPU on which we run our benchmark, it takes 7 seconds, And if you take the several cores and the whole CPU, you can get under 1 second to prove a transaction. There should be a slide there. Yeah. Thank you.
Thanks for the talk. We have time for a few questions.
Yes, thanks for the talk. So my question is more generic, where although you define that for asynchronous network, when I look at the cryptography and let's say distributed systems part, you can take the protocol and also make it work on a consensus rather than more like systems where transaction happen completely asynchronously. Am I correct in understanding that?
I'm sorry.
So you were more like a FastPay was one more paper where it goes back and forth between servers, but you can take your anonymous transaction and just post that on a blockchain, and still you'll get exact same properties, right? More like Zcash or other things.
That requires a lot of modification. Like the main advantage of the system is that it can work on asynchronous systems. Like it's basically based on sort of Byzantine reliable broadcast, consistent broadcast. So the main advantage is that we don't need consensus. So I think we would lose this advantage.
Oh, hi. I was just curious about the communication cost. So you said, okay, there are some improvements, but is it at the cost of communication?
Well, the communication cost, well, the transaction is just one gross 16 proof. So it's like 3 elements. And yeah, the public elements with the public inputs of the proofs.
And do you also prove this threshold blind signature part?
Yeah. We prove it within the zero knowledge proof. So we verify the
and this this threshold blind signature is not in the communication cost.
Yeah. You receive the signature. Okay. Of course, you send it to the validators, and then they sign the coin. And the only thing you receive actually is the signature, the partial signature.
Hey, so just quick question. I was trying to understand the architectural differences between the coins as they currently stand in your system and like Zcash / Penumbra style coins. So the two differences that I see is number one, and not for the regulated one, for just let's start with the standard one, is number one is you aggregate the blind signatures separately. So you have the send list, and that allows you to have this asynchronous network property, unlike Zcash, which will sign everything in a given block. And that's how you know it's like part of the nullifier set, right? Or not part of the nullifier set, I guess. And then I guess, yeah, how is it distinct other than that from the standard like way that the UTXO set works in Zcash or Penumbra, I guess? For like architecturally, how's it different from this PayPax version?
From Zcash?
Versus Zcash, yeah.
From Zcash, well, in Zcash, when you want to make a transfer, you prove that the old coins are kind of valid. To do so, you prove that they are included in a list of like a Merkle tree.
Like sorry, you're what? Sorry.
There is a Merkle tree of valid coins on Zcash, and you prove in the zero knowledge proof that the coins that you're spending are included in this Merkle tree. And this requires consensus by the way, because the Merkle tree is updated with each block.
Oh, I see. Here you have a got it, like a spent coin as opposed to having a available coin Merkle tree. Like here it's a spent list as opposed to like
here you don't use it. You replace it by just the certificate, the signatures, and the signatures make sure that the coin is valid. You don't prove like the. But this design is close to other payment system that was in the table. Like Zero Cash is supposed the very left because it's really the first one, like one of the first one that
for sure. Yeah, it was very reminiscent of that, so that's why I was curious and got it. And then the point is that this change now allows you to essentially have fully asynchronous settings, because now you can just aggregate the blind signatures yourself to prove that this is like a reasonable coin to be able to give you or something of the like.
Yeah.
Cool. Awesome. Cool. Thank you.